Okay, it's finally 10th week, spring quarter. This is the end is right there, right? 30 if you count, fall, winter, spring, you have 30 weeks of classes, or 33 weeks, and we're just at that final last bit, okay? If you were not here on Friday and you missed picking up a T-table or a formula sheet, you can come down and grab one, okay? Otherwise, you should have these. And okay, well, it looks like some of you guys need them. So yeah, come. You can pick those up, and then we'll get started on today's stuff. Let me talk a little bit about the final exam. Okay, so the final exam will be all multiple choice. And the, approximately 55 to 60 questions total. Okay, and this is kind of the approximate breakdown. Okay, so you can expect about 10 questions on conceptual topics for statistical inference. Okay, so that's chapters 7 through 9. Okay, you're going to expect approximately 5 questions on checking conditions for the central limit theorem. You can expect approximately 10 questions and this will be kind of that are definition based or conceptual for chapters 1 through 6, okay? So for chapters 1 through 6, we'll have a few definition-based or conceptual questions. Keep in mind there are no calculation-based questions for chapters 1 through 6. Okay, so students asking if it's cumulative, the answer is sort of, and there's 10 questions from chapters 1 through 6. But they're all definition or conceptual based. Okay, and then you can expect approximately 30 to 35 questions on statistical inference. Okay, and the questions on statistical inference will be similar to kind of your last quiz, except your last quiz was just based on proportions, and now we're going to have proportions and means mixed in, where I'm going to provide you some kind of scenario, description of a research question and data, and then I'll ask supplemental questions, things like, what are the hypotheses in this problem? What is your test statistic? What's the p-value? What kind of conclusion do you make? What's the standard error? All sorts of stuff regarding questions on statistical inference there. Okay, and then you'll have the full 3 hours. I anticipate most of you finishing within 2. Okay, are there any questions on this? I've posted a bunch of practice problems. Okay, so you have a practice final, and you also have practice problems for chapters 8 and 9. practice for chapters 8 and 9, along with conceptual practice too. So, work on those, and I think that will help you prepare for most of it, and then chapters 1 through 6, you'll probably want to go through your old lecture notes and just kind of review definitions and concepts there. Okay. Is that good? We're all good? Okay, so the last two topics I need to cover, these are the bottom two boxes on your formula sheet. Formula sheet will be provided on the final. Make sure you bring your tables though, okay? Bring your T-table and Z-table yourself. If you've lost yours, they are available on CCLE. You can just kind of download and print those out. You'll need the T and Z table. The formula sheet will be on the, I'll print it on the back side of the answer, your Scantron answer form. Okay, so we have, these are our last two topics. Hypothesis testing for mu based on one sample. And then we have hypothesis testing for mu1 and mu2 based on two samples. Okay. There are many parallels between hypothesis testing for mu as there are hypothesis testing for proportions. Okay, so if you are comfortable with hypothesis testing for P with one sample and hypothesis testing for P1 and P2 with two samples, then you're probably good to go for hypothesis testing with mu and mu1 and mu2 and all of this, okay? But we will we'll go through it and we'll do an example here, okay? All right, so we'll start off with hypothesis testing for mu based on one sample. Okay, and so what you need to do is you got to this is going to be for numeric variables or numeric variable. All right, we have the 4 steps, right? The 4 steps is what? Hypotheses, preparation, calculation, and conclusion. Okay. Same 4 steps. So we'll start off with hypotheses. Null hypothesis is going to be mu is equal to mu0, and the alternative hypothesis is that mu does not equal mu0, or mu is greater than mu0, or mu is less than mu0, okay? And again, the choice of not equal or greater than or less than for the alternative depends on how the question was written. Okay, so we've got all of this, and so for example, your null hypothesis might be mu is equal to 28, and in that case mu0 is 28. Okay, that's your hypotheses. Then we do our preparation. Okay, so we need to identify our data. The data pieces we need will be n, sample size, x bar, and s. Sample size, sample mean, sample standard deviation. Oh, and you'll also need mu0, the value in null hypothesis. It's not technically data, but you need to identify that. Okay, then you also select alpha, and you check conditions. One thing for numeric variables is checking the large sample condition works a little bit differently. It's not, don't sweat it too much, but okay, large sample condition, there's either two ways it's large enough, okay? If the population is normal, all sample sizes are large enough. Okay, so if you have a normal population, you can take a sample of size 3, and that's technically large enough, okay? If you have a normal population, all samples are large enough. If the population is not normal, or I'll just say otherwise, n should be over 25. And that's a rule of thumb, but okay. So if your population is not normal, then a sample that's 25 or more will be large enough. Okay. And for most cases, there are in some extreme cases, samples of 25 is still not big enough, but that's what we have. Okay, so that's checking checking your conditions. The other conditions are the same. Random and independent, big population, those conditions are still the same. Okay, let's talk about the calculations then. Okay, as far as calculations go, it's the same 3 steps. Standard error, test statistic, table. Okay, so say 3a, find your standard error. Standard error is given by s divided by the square root of n. Next, we're going to get our test statistic. In our case, because we're dealing with means, our test statistic is a t, and we do our observed minus what we expected divided by what? Divided by the standard error. So what we observed is x bar. What we expected if the null hypothesis were true was mu0. We divide that difference, the difference between the reality and expectation, by the standard error. This gives us our test statistic t. Okay, and now that we have this, we look up t in the t-table. Okay, the degrees of freedom is equal to n minus 1. Now, usage of the t-table is different from the z-table. So it will get its own few slides. So we go to the t-table and we're going to figure out our tail area, and then we're going to figure out our p-value. So standard error, test statistic, table. So you guys have this down. Can I flip to the next page? Okay, so we'll talk about using the t-table. Okay, So I'm going to say, let's pretend we've done the math already. So we've done the math, and we get t is equal to 2.56. We'll say t is equal to the value 2.56, and we have degrees of freedom equal to 11. We have 11 degrees of freedom. Okay, so what do? We're going to go to our t table. So let's see. So we're going to go to the, so I look at the column headings, okay, and then I go to the row for 11 degrees of freedom. So I'm just copying the relevant row here. So you need your row, and then you need the column headings, okay? So I'm looking at the row for 11 degrees of freedom, and I ask, okay, where does this value 2.56 fit, okay? Well, 2.56 fits in between here, okay? So 2.56 fits between t.025, which is 2.201, and t.010, which is 2.718. Okay, 2.56 fits there, which means my right tail probability is between these two values, okay? So the right tail probability is between 0.025 and 0.010. Okay, that's how it works. Our t is 2.56. It's between these two values in that row for 11 degrees of freedom, which means my corresponding right tail probability is between the column headings of 0.025 and 0.010. Okay, do you guys see that on your table? Everyone's looking at their table, and you can verify that. This is what the picture kind of looks like. So the t distribution pretty much is just like the normal distribution. So imagine you've got this normal distribution, and in the middle I have 0, and we're saying if I were to draw a line at the value 2.201, and if I shade everything to the right of 2.201, the amount I have shaded is going to be exactly 0.025, okay? So this area is equal to 0.025. The table also says that if I go further out to say 2.718, and I shade everything to the right there, then the amount I have shaded here, this area, is equal to 0.010. And so what I'm saying is, okay, what if I come to a value in between there, 2.56, and I want to shade everything to the right here? Okay, how much is this tail? Well, the answer is we do not know the exact tail area, okay? Exact area of the tail to the right of 2.56. But we do know it must be between 0.010 and 0.025. Okay? And that's what we do. We just say, okay, I don't know the exact value, but I do know that 2.56 is in between these two values. Therefore, my tail must be between these two values. So I can just say tail is between 0.010 and 0.025. I can write it this way. My tail, whatever it is, I don't know exactly what it is, but I know it's between 1% and 2.5%. Is that okay? All right, let me copy this. All right, so let me give you a clicker question to check your understanding here. Okay, so let's say, so again, pretend we've done the math. Okay, we'll say degrees of freedom is equal to 11, and we'll say t is equal to 4.79. Okay, and the question is, how much is the right tail probability? Okay, and so here are your answer choices. You have okay, let me get this session started. Okay, 11 degrees of freedom. You have your t is 4.79, and the question is, how much is the right tail probability? Okay, if you need to consult with your neighbor, you can. All right, let's take a look at how you guys responded. Okay, and the answer is indeed C. It is the tail is less than 0.001. Okay, because when we look at this, we see, okay, the value 4.79 is over here, which means the corresponding tail has to also be over here. What we see is that over here, you know, we're small and large, but if we look at the tail is large here, and the tail is small here. So as we go farther that way, it gets smaller. So, you know, you can imagine kind of the right side of the normal distribution, and the idea here is that if I drew a line at 4.025 and I shade everything to the right here, the area here is only 0.001. Okay, this area, the green area, is 0.001, and the question is, okay, if I go even further out to 4.79 and I shade everything to the right of that, how much will I have shaded? Okay, well, that area, whatever it is, the tail here, this tail must be less than 0.001, whatever it is. Okay, and so that's our answer. We don't know exactly what it is, but we do know for a fact that it is less than 0.001. Okay, so this, so you have that, and let me just kind of make a few more notes. Okay, if so, just on the other side, let's say degrees of freedom is equal to 11, and t is equal to, I don't know, 0.85, then in this case, t equal to 0.85 goes right there, and then that means your corresponding tail, whatever it is, has to be greater than 0.1. So the tail, whatever it is, has to be greater than 0.100. Okay. The table is symmetric. Or not the table, the t distribution is symmetric. Okay, the t distribution is symmetric. So if we get a negative t-value, okay, we can still look it up in the table. So what do we do with a negative t-score? Okay, what you do is, so let's say degrees of freedom is equal to 11, and so we're still using the same. What's going on here? Okay, so degrees of freedom equal to 11, and let's say t is equal to negative 1.95. Okay, well, what you do is you just drop the negative, drop the negative sign, and look up t equal to 1.95. But then you make a mental note, and you say, okay, well, I don't have the right tail probability. Now I have the left tail probability. Okay, drop the negative sign, look up t equals positive 1.95, but make a note that the values are now left tail probabilities. Okay, is that good? So tail is greater than 0.01, so this is technically a right tail. And over here, what we would have is, okay, well, 1.95 goes there, so that means my left tail is for sure between 0.025 and 0.050. Okay, I don't have an exact value, but I do know my left tail is between 0.05 and 0.025. All right, is this okay? Getting the tail area from the t-table. Okay, so once you have this, then the next thing we do, so we're still in part 3C, part of the calculation to get a p-value. So what we did was you look up t in the table, you get your tail area. And now you go from the tail to a p-value, okay? And now we get our p-value. And the rules for the p-value is very similar to before, okay? If the null hypothesis has a greater than sign, then the p-value is equal to the right tail area. If the null hypothesis has a less than sign, then the p-value is equal to what? The left tail area. I'm hoping this sounds somewhat familiar or similar to what we've seen before. And if the null hypothesis has a not equal sign, what do we do? The p-value is equal to 2 times the tail area, whether it's left or right. Okay, 2 times the tail area, you know, either left or right. Okay, it's just 2 times the tail area. Okay, that gives you your p-value, and now that you have a p-value, what is the last thing we do? Make a conclusion. And how do we make a conclusion? Okay, well, if the p-value, these are the same conclusions as before. If the p-value is greater than alpha, what do? We do not reject what? The null hypothesis. And if the p-value is less than alpha, we do reject the null hypothesis. Yes?
Alpha set at 0.05 as usual.
If alpha is not specified in the problem, assume that it's 5%. Otherwise, use whatever the problem says for your significance level. So the problem might say, use a significance level of 10%, and you would use that. Yes?
To get the p-values, why is it like if null hypothesis also is not 10? Why is it not if the alternative?
Oh, I'm sorry. That's a good. You are absolutely correct.
What was the question?
Why did I write the wrong thing? And okay, and it's because I made a mistake. So it's if the alternative hypothesis. I'm sorry, I've been saying the wrong thing. Okay, if the alternative hypothesis has a greater than sign, or the alternative has a less than sign, or the alternative has a not equal sign, that's what we have. Because the null hypothesis always has the equal sign. So sorry, that was a mistake. Thank you for catching that. Okay. All right, is this good? Okay. I'm going to go ahead and just show the steps for doing hypothesis test for 2 samples, and then we'll try out an example. All right, so the other topic, hypothesis test for means for mu1 and mu2 with 2 samples. All right, the null hypothesis in this case is mu1 is equal to mu2, okay? Can also be written, how can this also be written? It can be written as mu1 minus mu2 is equal to 0, yeah? And then the alternative will be mu1 is not equal to mu2, or mu1 is greater than mu2, or mu1 is less than mu2, okay? Also be written as mu1 minus mu2 is not equal to 0, is greater than 0, or is less than 0, okay? Those are your hypotheses. Preparation. All right, we need to identify our data. Okay, so you're going to have to identify one as sample 1 and the other as sample 2. Sample 1, you will need N1, X bar 1, and S1. Sample 2, you need N2, X bar 2, and S2. That's the pieces you need. Select alpha. Okay, default level is 5%. But if the problem says use a different alpha, use that alpha. And then check conditions. This part's still good. And then we'll do our calculations. Okay, this is all, it's all written on your formula sheet, okay? Your null hypothesis and all of this. All right, calculations. So, standard error, test statistic, table. Standard error. S1 squared over N1 plus S2 squared over N2. That's what we do. Now we want the test statistic. Test statistic is always in the form. Statistic is going to be T is in the form of what we observed. It's reality versus expectation, right? Observed versus what we expected divided by the standard error. What we observed was the difference between X bar 1 minus X bar 2. This is what we observed. If the null hypothesis were true, what would we expect the difference between X bar 1 and X bar 2 to be? we would expect that difference to be 0, okay? And so we say what we observed minus what we expected divided by the standard error. So subtracting 0 just simplifies things, and we just have x bar 1 minus x bar 2. And we're going to take that difference and divide by the standard error. So this is our test statistic t. And then part 3c is we look up t in the table. You get your tail area, and then you get your p-value using the same rules as before, okay? If the alternative has a greater than sign, right. If the alternative has a less than sign, to the left tail. And if it has a not equal, you multiply the tail area by 2. I don't need to write all that down again, right? You get like... Okay, and then 4, we make our conclusion. And this is the same as before, right? If p-value is greater than alpha, do not reject the null. And if the p-value is less than alpha, reject the null. Okay, is that good? All right, let's try a problem, an example out. All right, I'm gonna flip the slide here. Okay, we'll say in 2015 we surveyed, I don't know, we'll say 25 random people, and we asked how many text messages do you send a month? Okay, I don't know. It's random people, so I don't know how many texts random people send. All right, we'll just say the average is, I don't know, 350, and the standard deviation is 75, okay? And then in 2017, we surveyed 30 random people. We asked same question, okay? And we'll say the average is 375, and the standard deviation is 80. Okay, and so the question is, does our data provide evidence that the number of texts sent per month has changed between 2015 and 2017? Okay. All right, so survey in 2015, the average was 350. Survey in 2017, the average is 375, okay? So the number has increased by 25 on average. Is that evidence that there is a difference? Okay? So we're going to do a test. Our null hypothesis will be what? Mu1 is equal to mu2, and the alternative will be that mu1 is not equal to mu2, because here it says changed. Changed means not not the same. Means not equal, okay? What if it said has increased between 2015 and 2017? So if so increased from 2015 to 2017. So then the alternative would be that mu1 is less than mu2, right? Because mu2 represents 2017, mu1 would be 2015, so this we would call this sample 1, and this is sample 2. So if we expect 2017 to be larger, to have an increased since 2015, we would expect mu1 to be less than mu2. Is that good? All right. So let's go ahead and we'll label all of our pieces n1, x bar 1, and s1, and n2, x bar 2, and s2. Okay. n1 we go through, and I have 25. X bar 1, 350. S1, 75. N2 is 30. X bar 2, 375. And S2, 80. Okay, so we've gone through, we've identified our data. We'd probably need to check our conditions in all of this, but actually we got samples of 25 or more, so we're probably good. Okay? Is all right? So now we'll go ahead and we'll do our calculations. I guess I could have made a clicker question in one of these things, but it's all right. We won't. Okay, so we got S1 squared over N1. S2 squared over N2. This becomes a square root of 75 squared divided by 25 plus 80 squared divided by 30. When I punch this into my calculator, what do I get? I get 75 squared divided by 25 plus 80 squared divided by 30. I get 20.936. Okay. And now I ask, what is my test statistic? Test, it will be x bar 1 minus x bar 2 divided by the standard error. I have 350 minus 375 divided by 20.936. This gives me 1.194. How many degrees of freedom do I have? N minus 1, use the smaller n. I got negative 1.194, yeah. Use the smaller n. Okay, so I have 24 degrees of freedom. Okay, degrees of freedom is equal to 24. I have negative, and t is equal to negative 1.194. So I go to my t-table. I go to 24 degrees of freedom. And the values I see here are right here, this row. Okay, which means that my corresponding left tail area, has to be what? More than 0.10. Okay, so I got 1.194 is right here. This is my left tail area. So my left tail is greater than 0.100. What we noted is that the alternative has a not equal sign. So our p-value is equal to 2 times the tail. So that means my p-value, whatever it is going to be greater than 2 times 0.100 or 0.200. And this is my p-value. My p-value, whatever it is greater than 0.200 because I double my tail area. Is that okay? All right, and then so if this is my p-value, then my conclusion will be do not reject the null hypothesis. And we say we do not have evidence that monthly texts have increased, okay? Okay, we'll end there. We'll see you guys on Wednesday.